Cars capable of autonomous driving are starting to take over the industry. But how confident are we in their capabilities? Do we really trust them? Well, we don't think so, at least not yet. So this is where our project comes in. Our goal is to design and build a research platform that has multiple sensors that resemble those on real-size autonomous cars. The goal is to have a research platform in testing many autonomous driving applications. I am Omar Abbas, and I was responsible for integrating some of our hardware components and software applications with their dependencies in our Linux-based platform. I was also responsible for documentation and our site, supercomo.com.
My name is Abbas Bajachari, and I was responsible for building our microcontroller subsystem and also implementing the software for our low-level sensors.
My name is Jocelyn Leonidas. I worked on researching the hardware components and designed the CAD files for the decks and the hardware mounts.
Hi, my name is Ridwan Giwa, and I worked on the hardware components and circuit design for the microcontroller subsystems. Our project is divided into three main parts: hardware development, software integration, and experimental validation. Our platform is made unique with the multiple sensors that's incorporated into the project. This gives the researcher or the user flexibility in the type of autonomous algorithm he develops. Our project consists of multiple cameras, LiDAR, GPS, IMU, ultrasonic sensors, and even a wheel encoder. And all this real-time devices then sends data into our AI embedded computer called the NVIDIA Jetson TX2.
The sensors, the microprocessors, and the electronic speed controllers must operate together to perform autonomous driving features. For that, we use the Robot Operating System Framework, ROS, on Linux to facilitate the communication between these components. All of our documentations, including the CAD files and the ROS packages, are all open source and available on our website.
To demonstrate our platform, we perform several key autonomous self-driving features. Our car can do line following, where it uses a camera to detect a white line and follows it. Our car can do hallway navigation, where it uses a LiDAR to trace the wall to its left. It can do collision avoidance, where it stops if there's an object in front of it. And it can do object recognition, where it employs machine learning algorithms to detect and recognize objects such as stop signs. Our final design is a powerful and reliable testbed with well over 98% platform success rate and well over 3 hours of operation time. Our car is currently being used by Professor Dr. Tyler Summers at UT Dallas for his research into autonomous self-driving. Thank you, and now I'd like to open the floor to questions.
You mentioned that 94% success on trials for this navigation. If you want to achieve more than 94, what you have to do with it?
Currently, the 94% is because we were also testing it outdoors, and in an outdoor environment, there's a lot of obstacles that we didn't foresee, and that sort of led up to why our research platform didn't perform as we had really thought it would. So that would take more calibration into how we can use our sensors to better calibrate them into our outdoor system. Majority of our testing was mainly done in our lab. Inside, indoor, we had the lighting correct. We had all our cameras configured to the indoor lighting. So whenever we took it outdoors, the lighting was totally different, and it wasn't calibrated to that. So it's going to take a little bit more calibration into outdoors, and definitely we'll be looking more into using a different sensor package. Like we were using LiDARs mainly indoors, but maybe outdoors the ultrasonic sensors would be better. So that would require more calibration. Yes.
I mean, you won't get all environment conditions here in Dallas. What will you do if you want to deploy in a different part of the world to test these conditions?
Are you saying like outdoor conditions in a different location?
Right. I mean, if you have to test it and you won't get all environmental conditions in Dallas, what ideas would you have in mind to actually test this?
Definitely. Well, this research platform is mainly for like indoor applications, but for outdoor applications, we're definitely looking forward into calibrating the sensors, as I said before. So let's just say Dallas is a very hot, humid area where it's mainly flat, right? The land is it's very flat. We don't have any hills or mountains here, so we don't really have to deal with having to go in a incline or maybe there's like sharp edges or something. But we do have an IMU incorporated in our research platform, which helps with the positioning of the robot and the alignment. And then that is more of a, you could build a system that can use that IMU data and then help you calibrate your robot so it can move in a more mountainous or like a hilly environment.
Did your 6% failure, did you take plans on how to correct the 6%?
Yes, the 6% would be further calibration into like outdoor environments. So it would be more into like, we really were focusing on indoor, and then we also tested it outdoor, and it would be just using a different sensor package. Because right now our hallway navigation algorithm is mainly just using a LiDAR for distance calculation. Maybe ultrasonic sensors would be better for that. So that's all up to the user and how they want to use the research platform.